Hi, I'm Isabel.
And I'm Tony.
And today we will be introducing you guys to the concepts and techniques of special relativity. We'll be doing this by guiding you guys through a seemingly unsolvable paradox.
We will begin with a brief introduction to reference frames and special relativity in general, and we'll explain key concepts as they become pertinent to solving the paradox.
Let's get started.
Let's talk about inertial reference frames. An inertial reference frame is a frame of reference that describes time and distance independently. An inertial reference frame can be moving with constant velocity or at rest. However, it cannot be accelerating. There can be infinitely many inertial reference frames to describe the same event or motion. Let's take a look at an example. Let's look at the example of a train passing by a station at 10 meters per second. Here we have two inertial reference frames depicted using world lines. World lines are similar to distance versus time graphs. Here, from the perspective of the station, the train moves 10 meters in 1 second. However, someone on the train does not perceive the train as moving relative to them, so it moves with 0 meters per second. Special relativity may seem like an intimidating term. However, it is merely a fancy way of talking about how time and space behave differently at very high velocity. That brings us to the paradox. Let's say there are two twins that hop into spacecrafts and turn on their spacecraft at the same time. One is 100 meters ahead of the other. They accelerate away from the Earth until they both run out of fuel and continue to coast at a constant velocity. From the perspective of the parents down on Earth, the twins are still 100 meters apart and are both the same age. However, the twin in the front is older. Why is this happening? One would think that since they start off in the same inertial reference frame and accelerate, then re-enter the inertial reference frame once they are at a constant velocity, that the twins' clocks would still be at the same time because they're the same inertial reference frame. This has to do with the loss of synchronization. Essentially, their clocks have become out of sync and are showing different times. This is because of the acceleration. When clocks undergo acceleration, they are no longer in an inertial reference frame, and thus, when they re-enter an inertial reference frame, will show different times.
Let's get to solving this problem. First, we need to look at the world lines in the home frame. So here we have the home frame, and we see that Alice and Bob start 100 meters from each other, accelerate at the same rate, and then at some time, both their fuel runs out and they start coasting at a constant velocity. So once we understand this, we need to translate that to the reference frame of Alice and Bob. How do we do this? We do this using a double observer diagram. So this is where we have this new x prime and t prime axis. That is helping us establish the reference frame of Alice and Bob. How do we calculate this angle between these new axes? That is tan phi equals beta, where beta is the relative velocity of the spaceships to the home frame. So we can still see that the parents from Earth, from this home frame, see that Alice and Bob are the same age. However, is that true in their reference frame? So how do we read this graph? In a normal graph, where the axes are perpendicular, you typically drop down a perpendicular line from the point. However, we can't do this when the axes aren't perpendicular. Instead, we're going to drop down a line that's parallel to this other axis. So when we do this in our diagram, we're going to be dropping a line that's parallel to this x prime axis. So we'll start with Bob, and then Alice. So we can see that in their reference frame on this t prime axis, they're not intersecting t prime at the same point. There should be some difference between their time. How do we actually figure this out? This is where Lorenz equations come in. Lorenz equations are a series of equations that let us move back and forth between different inertial reference frames. So we're concerned with t prime, where t prime is going to be the time in Alice and Bob's reference frame. So this is an equation that relates t prime to beta, which is that relative velocity, t, which is the time in the home frame, and x, which is the distance in the home frame. So what we're really looking at is the difference between Alice's time in her reference frame and Bob's time in that same reference frame. Okay, so now that we know what we're looking for, the time in Alice's reference frame minus the time in Bob's reference frame, and we know the equation that can tell us that, let's plug in some numbers. Let's say beta, which is that relative velocity, is 0.9. So again, that means that they're moving at 9/10 the speed of light. We also know that the distance between them in the home frame is 100 meters. Now, we also could know time, but that actually ends up canceling. So, when we plug this all in, we get that the time difference, delta t prime, is going to be 6.87 times 10 to the negative 7 seconds. So although very small, there still is a difference. Alice will look at Bob and see that he is younger, and Bob will look at Alice and see that she is older.
Therefore, due to the constraints that even though the parents on Earth see the twins as 100 meters apart, the twins are no longer twins.